Here in this video I'll show you how alternator works.
If you push a current of electrons through a wire, a magnetic field is made. And if you coil that wire up around an iron core, the effect gets way stronger. You've just made an electromagnet. And it also works in reverse. If you move a magnetic field relative to a wire, the field nudges on the free electrons, making them want to move, aka voltage. And if you allow them to move by completing the circuit, the electrons that are being pushed are now able to flow. This is a brushless outrunner electric motor, and it has permanent magnets arranged around the outside, which spins around the coils of wire in the middle. When I spin the magnets relative to the coils of wire, there is a voltage produced in those coils. But there is no power being generated because none is being used. The leads are not connected to anything, and the motor, or in this case the generator, is very easy to move. However, if I touch the leads of wires together and short them out, there is very little resistance, and the super small voltage I'm generating is now able to flow. And when there is voltage and the current can flow, now that is electrical energy. The motor now becomes very hard to turn because the electrical load causes a physical load on the power source, me. You didn't think the energy came from nowhere, right? We are just transforming my kinetic energy into electrical energy and then into heat. And if I connected the leads through a load with a lot more resistance, less current would be able to flow, and thus less power would be consumed and the motor would be easier to spin. The thing about electrical equipment, like those in your car, is that they tend to run off of a narrow range of voltages. So, what determines what voltage will be created by a generator? I've broken it down into three basic components. 1. The physical thing, as in like the size and the build quality, the turns of wire, those kinds of things. The second thing is the speed that the rotating magnetic field runs at, so RPM. And the third thing is the strength of that rotating magnetic field. So the faster I spin this motor, which has fixed physical characteristics and permanent magnets, the higher the voltage will be. The thing about cars and airplanes though is that most of them run off of 14 volts, but since the alternator is driven directly by the engine, which by the way changes RPMs all the time, how do we regulate the voltage? We can't really change the first one. The speed is determined by the engine, which changes all the time in vehicles, but we can change the strength of the magnetic field if we use an electromagnet, and that's exactly what they do. This is an old aircraft alternator cutaway that I made for a class project. You can see the pulley where the belt goes, which is also the cooling impeller, which flings air out centrifugally, causing more air to be sucked through the alternator. The rotor shaft is being supported by a bearing, and this is the rotor. It's called that because it rotates, and it's just a big electromagnet in the center. The ring of coiled wire on the outside is called the stator because it's stationary, and the stator coils go to the three-phase rectifier. There are 6 big diodes which are used to rectify the alternator's three-phase AC output into DC for the vehicle's electrical system. This is the positive bus that I painted red. It has 3 diodes on it, and every time a wire goes positive, it goes here. And the other one is the negative bus, which I painted black, where every time a wire goes negative, current returns through that bus. The positive bus has a bolt that sticks out and is insulated here, and the negative bus has a bolt that sticks out but is not insulated, so the alternator housing is also grounded. The electromagnet rotor in this alternator, which they call the field winding, is powered through this plug here. These 2 prongs go to some carbon brushes which are spring-loaded to contact these 2 copper rings. This way we can power the magnet even when it's spinning. But how do we control how big the magnetic field is, or even know how big to make it? I got this weed whacker motor from a yard sale for $10 and it didn't work. I just thought it was the coolest thing because it's a miniature 4-stroke engine to play with. I took it apart and cleaned it up and figured out how it worked, and then I put it all back together. This is another aircraft alternator which was unairworthy, but apparently still functional to some extent. In order to drive the alternator with this engine, I machined an aluminum pulley adapter on a lathe to fit this pulley I found. And I also made this little ring to inlay this magnet into so that I could use this battery-powered electronic ignition system on the motor. Every time the magnet passes the Hall effect sensor, the spark plug fires. Alright, so I made this simple alternator controller out of an Arduino and this little breadboard that I used to hold 2 simple circuits. I needed a way for the Arduino to sense what voltage the alternator is outputting, but the Arduino can only sense between 0 and 5 volts, and I want this alternator to be producing around 14 volts. So I made this simple voltage divider circuit to scale the possible output voltages into a range between 0 and 5 volts. It's just two resistors connected to the alternator output in series, and in the middle of the two is where I'll take my voltage readings from for the Arduino. That wire goes to pin A0. So that was the sensing circuit, and this is the control circuit. All it is a switch that can turn on and off the field winding. I'm just using a large transistor mounted to a random bar of aluminum for thermal dissipation. The alternator output is connected to the field winding through the transistor. A transistor is basically just a solid-state electronic on-off switch. The transistor is controlled by the Arduino through this wire, which is connected to pin 13 on the Arduino. Pin 13 also happens to have its own LED, so we can see when it's on and off. And here's the code I wrote to control the whole thing. If the alternator output is below the 14 something volts that I want, which I will now call the threshold, then the field winding is turned on. If, because the engine spins up, the alternator output goes above the threshold, then it turns off the field winding. And that's all it does. So let's start this thing. Normally, an alternator needs a small power source to get the whole thing going, but the small current going from pin 13 is actually going through the field winding to ground, so this works too. Once it goes past the threshold of just over 14 volts, the Arduino will turn off pin 13, and the magnetic field will shrink, and the output will dip below the threshold, and then the Arduino will turn back on, and then the field will grow, and the output will increase above the threshold, and so on and so on. And so it's basically just switching on and off really, really fast, regulating the voltage right where I want it, with varying engine speeds. This is kind of like it's forming its own square wave pulse width modulated type signal or something to vary the voltage. Another thing to note is that when you apply an electrical load to the alternator, it becomes harder to spin, and it bogs down my engine very easily. So I guess just for fun, I'm gonna just take this whole engine apart and show you how it works if you want to stay and watch. I didn't want to make this video any longer, so I've uploaded it as a separate unlisted video that you can only get to by clicking this link here or in the description.